Hello. Hi guys, good morning. Ki halchal sab changa si. I hope that you guys are doing good. Firstly, I swear this video is gonna be insane according to the intuition. Also, like you might have studied this same Morris Traversal thing in the past, but for sure you might have just forgotten or okay, what was the flow like. But after this video, never ever you're gonna forget what was Morris Traversal and how the entire we'll go on from the entire linking from not doing anything to just deriving everything out. I'm not saying just okay, I'll just show you trial and all that stuff. We will do that for sure, but the more important part is to go through the intuition, how we reach. If we think that 8 months down the line we will not remember that, then how we will pick this problem. Cool. Now let's see, it is just binary tree in order traversal. We will see all the traversals. No worries if you have not known anything whatsoever I have spoken previously, but still it just says that we have to do in order traversal. We will see what that is. It just says that given the root of a binary tree, return the in order traversal of its node value. Now it has been asked by Amazon, Adobe, Uber quite a lot in the last 6 months, and in last 1 year by Microsoft, Google, Facebook, Apple, Yahoo. Like it's kind of frequent question for the Faang companies. Now let's come on to what is this binary in order traversal. So it's just a tree. Firstly, it's not a graph, it's a tree, and it's an in order traversal. So basically we have 3 kind of traversals. First one is a pre-order traversal, as the name itself says, pre. So the node will come previous, like it will come pre. In order, there is no, as you can see, so it is just in between. Node will come in between. Post, the node will come post. The node will come post, and for sure you will see the remaining left and right will be sequential. Now for sure you will have a node or a left or right. Left and right will always be sequential, left and then right, left and then right. So for sure left right, left right, left right, right. So that's how you can just, from the wording itself, you can make this diagram. Okay, if it's a pre-order traversal, which means I will first write my pre, which is node, in the beginning, and then I'll write my left and right. If I have in order, which means I'll write my node in between and then left and right. If I have a post order traversal, I'll write post I'll write node, which is the node in the post, which is in the end, and then I'll write left and right. Now as simple as that. Whenever you are doing any of the tree traversal, your favorite partner is recursion, or basically simple DFS. Now you know that you have to do a in order traversal, what the question asks, but with this same we can derive other traversals also. How simple as that. Now you just have to traverse the firstly you have to traverse the left child, then node, and then the right child, which means if you have a tree like this, you have to go to the left. Okay, now I am at the left. Now use and print the left. Okay, I'll print the left. Now okay, left is done. Now for sure comes the part of the node. Okay, node will be done. Okay, I'll just do the node because left is done. Okay, now the node is done. Now go to the right, which is 4 and 5. Okay, 4 and 5. Okay, now right is also done. But now the left is now done still. Okay, now do the node. Okay, I'll do the node. Oh, now go to the right. Okay, I'll do the right. So that is how you will get the in order traversal of this tree. Simple as you saw. I firstly went on to the left, printed. Okay, as soon as I reached the extreme left, I printed the node, and then I moved on back. And see, moving back is very easy in case of recursion, because recursion stores, okay, if you were coming from 1, then 2, then 3, you have reached. Now you cannot go anywhere in the left because your prime purpose was to go to left. Now you cannot go anywhere in the left. So for sure recursion will backtrack itself and will bring you back to 2. Now from 2 you can go back to 4 and then 5. This backtracking, as in moving back to the previous node, root node, that is handled by recursion by itself, because it keeps these addresses in its memory, so that when you are coming back, you know where to come back. And that is the improvisation we will take. Let's see what we will take. But yeah, right now you will see that if the node is not equal to null, as in as far as you can go to a node, you will keep on going to a node. Firstly, you will try to go, like just forget and remember this as a function. It's a function where in the recursion you are saying, bro, recursion bro, please go on, keep on going to the left, keep on going to the left. So recursion will keep on going to the left. As soon as it has reached the extreme left, it needs to print or basically push the value or basically do any operation on that in order traversal whatsoever you want. So I'll do the operation on the value of the node because I have got the node, and then now as soon as I've got the node itself, which means I have iterated on the left, I have got the node, I'll go on the right. That is what we saw also, left, node and right, and simply no worries, recursion will handle everything for you. You go to left, you go to node, you go to right. And same if you had the pre-order, so node and then left and then right. If you had a post order, then left, right and then the node. That is how easily recursion can handle everything for you. If we go and want to have a look at the code, then let's quickly have a look at the code, and the code will be extremely same, exactly same as what we have seen for others also. So as you saw that we need to return the entire traversal for the entire thing, which means the entire tree. So I will have the answer which will store the entire Preorder traversal for my node. Now as you know that I can write the same function as solve also, or here we are doing a Preorder traversal, so I can write Preorder traversal as a function, just a function name. Now I'll pass my root node because it is a starting node, and I'll pass my answer. Now when I know that my Preorder traversal will in memory assign the nodes, and I can simply return the answer. Now I'll just go and now apply my Preorder traversal. I know that I have to start off from this node. I can name this node as anything. Let's say I name as current. I can name it as node also, anything whatsoever you want. Usually I either choose node or current, and here you will see I'll pass my vector as an address because I'll keep on assigning in my address itself, in my answer vector itself. Now as you saw that if this node is not equals to your null PTR, which means, or you can also write the null with all caps in C++ and null in Java in all small. Now if it is not equal to null, which means now I can actually go, which means I'll keep on going and try to go on to extreme left, which means I'll firstly go left. This recursion will handle going left, and then when my left portion is done, now I will have to process my node itself. So, and process as in I just have to push the value in my vector. So I'll just push that corresponding value. Now when this portion of value is done, I know that okay, now I have to process my post as in right. So I'll just do and process my right, and that's it. Rest all is handled by recursion itself, and then I can just simply run to check if there's no pre-order of, okay, we have to pass an answer also because everything we are passing as an answer. And yeah, so with this you will see that answer or pushback node value. Okay, now with this you will see that we are simply solving and the recursion will handle this. But if you go back and see, its time is O of n because for sure you are iterating on all the nodes. Now when I am saying iterating, what will happen? See, if you have this node, let's imagine this as a tree itself for me. So if I just quickly copy this up for you guys, and now what will happen is that, sorry, yeah. So what can simply happen is it will just simply start off from this 2 and then 3. Okay, from here it will print 3, come back 2 and print 2, go to 4, go to 5. Okay, come back 1, go to 6, and then simply an end. So you saw I'm just iterating on all the nodes just twice, going down and then going up. So it's O of n plus O of n, that's it. So time is O of n. But you saw that this recursion, because if you are going and the recursive stack will store, okay, 1 and then 2 and then 3, which means after kind of a recursive stack which is being built while we do DFS. So it will come back, it will just use 2, then it will build the recursive track for 4, 5. So you see that in the worst case it can be like squeeze, so it can go up to O of n of space in the worst case itself. So yeah, your recursive depth is actually O of n, so your space is also O of n. Now that is the standard solution which you can do apply for anything, but the interviewer will follow up with other problem. Firstly, there is another way to solve it by using stack, which is iterative, but you saw that the thing which recursion is doing for you by itself, you have to do it manually by using a stack, which means keeping track, pushing on values, popping out values and all that stuff, the same way I showed here. But still the time and space will be O of n and O of n itself. Now comes a part where the interviewer will ask you, please optimize this. How will you optimize that? Now comes the part of Morris Traversal. Now forget this F word. forget this word itself, you don't know what it is, and just simply see how we will start off what we want. Again, our main thing is to optimize this. For sure, you have to print the entire traversal, so time is something which you will keep O of n itself, you cannot optimize that. But space, maybe if we are using a recursive stack, maybe that is not useful, so maybe we can optimize the space itself. That is one option for us to optimize. Now we have known, okay, we have an intuition of what we can optimize. Now let's see how actually we will optimize that. Again, forget this word, but still, as for your remembering, if anyone asks you a bit of what is Morris Traversal, so you know, okay, what we are learning right now is actually known as Morris Traversal, but we will not know anything. We will go from very scratch. Now, very scratch as in build the example small by small. Let's say if I ask you if you only had just one node, value 1. Okay, now what you will do, I ask you print the in-order traversal, you will just simply print this node value. That's it. Now if I ask you, bro, no worries, now you have one more node. Okay, I had one previously, I have one more node as in 6. Now if I ask you print the in-order traversal, you will print the node and then you will simply go on the right child and then you can print again. That is how you will work. As simple as that. Now that is also okay, which means you saw that we can just simply keep on like printing the nodes. That's it. Like I'll print 1, I'll go on right, I'll print 6, I'll print 1. So it is right now, it's just printing a node, going right and printing a node. But now comes the interesting part. I increase my example a bit more and you will see I am just making my example small by small. Here you saw just one node, simply print that node. Here you have two nodes, print that node and go on to left and go to right child and then print that node. Okay, that is simple done. But now comes the interesting part. Now I have one more node. Now what to do? So you will see that how you have to perform this. You will see, firstly, you will write down, okay, the in-order traversal for this example, which we have thought of right now, should have been a 216, which means I have to go on to 2, then I have to go on to 1 back. Now that is the interesting part. Going on back to 1 was handled by recursion by itself, and if you have used a stack, so it would have done, okay, use 1 and then use 2. But then now you cannot use a stack, you have to build this connection from 2 to 1 by yourself. That is the interesting part, which you have to go and build by yourself. So what you can think of doing is, bro, acha, okay, so what you only want from me is, okay, as I go on to my left, I have to build a connection to my previous node from where I came. That is what you wanted. Maybe it is true, maybe not, but yeah, that is what we wanted. I go on to left and I want to build a connection. Again, I'm saying I have to go to, because it's just, the example is small. We have to still go on to the better example, but right now with this current example, we know one thing, that okay, as we go on to left, we have to build a connection to the root node somehow. So what we can do is, okay, we can just build a connection to the root node. But bro, if you build a connection to the root node and if it is a cycle, because you know that if it is like this, so you will keep on looping in this cycle, infinite loop. So that might end up in an infinite loop. So also you would never need this connection. If you are at 1, you know 2, you have built this connection, so you would never need this 1-2 connection. You can have address of this 2 and this 1 also. So for sure, you can just remove this connection. Now your final tree would look something like this: 2, 1 and 6, and for sure it is 1 to 6. Now earlier your tree was 1 to 2 to 6 and you are confused how to travel and stuff. Now your tree is like this: 2, 1, 6. Now simply print 2, print 1, print 6. As simple as that. Print 2, print 1, print 6. So again, it is just that now we have to just simply traverse. That's it. That is the amazing part. What we did, we just have to build a connection. That's it. Now how we build the connection? Now let's recap how we build the connection. Firstly, we were at this node, at this root node, which is the node itself. Now I'll replace this node by the name of current in the code itself. But right now, let's say it is a node, because for you it is a node. 1 was a node which you are standing right now, because you know that you build the example by 1 and then 6. Your node was always at 1, starting from 1. Now you were at 1. You had to, by this example, by this current example, you had to go to left. Again, by this current example, right now, with a small example, you have to go to left, and then with that left, you had to build a connection to the node, current node itself. So what I will do is, I will firstly go on to my left, and I cannot lose this current address, which is the node address. So I'll keep node, I'll make another pointer as pre, or basically name as previous or pre, anything you can name it as. With this pre pointer, I'll go on to my left node. So I'll just did simple one thing. I went on to my left node. As you can see, I just simply went onto my left node, and maybe I have to perform something else if the tree is big. Maybe that I don't know right now, but still I went on to left and got this particular pre address, and I remembered with this pre address I have to point this pre to my node. I'll point this pre's right. Again, it is you will say it's pre's right. I'll point my pre's right to the current node. Okay, now that is done, but you remember the issue with this. It will form an infinite cycle, or basically a loop kind of, right? So what you have to do is you have to remove this particular edge as it is from this node. You have to remove this edge. That is what you wanted, but still you know pre, you know this node, so, and your main iterator on this entire tree is the node. So firstly, make sure that you move this node to the left node itself, because you are about to remove this edge from 1 to 2. You are about to remove this edge from 1 to 2. So please move this node from 1 to 2 itself, so that you maintain your node itself. So what I will do is, now if I just move my node, I have to also make sure that once left I have to remove also. So I have to also keep track of 1, I have to also keep track of 2. So what I'll do is, one way is I can move directly to my left node, but before that I'll assign a temp variable to 1. So what I did was I made a new pointer temp and assigned it to node. So node was here itself. Now the temp is also at 1. Okay, and then I moved my temp, I moved my node here. So my node was moved to the left. Okay, now my node is at 2, and then for sure temp's left needs to be null. So I'll just do temp's left. Temp is this, it's left, it needs to be a null. That's how you will just simply block that connection, so that, because you have reached here. Now ultimately in future, whenever you want to reach 1, you can go via this path from 2 to 1, and that's a good path, because for you only need that specific traversal from 2 to 1. And ultimately that is how you can easily build a connection. Now okay, with this small example we have built that we'll firstly make a pre node, which is just left node of the root node of the node itself, and then from that pre's right I'll make, maybe I have to do something in between, I'll see that, but from that pre's right I'll point to that node. I want to remove the connection, but for that I have to first assign the temp to the node, and then move your node to the left, and then assign your temp's left to null. Now this portion is done, but that was for the small example. Again, make the example much more bigger. So I'll go on to my base example, which is the root example. What I learned previously was, from 1 I went on to my left, and then from left I just build a connection to the node itself. So if I ask you, was it correct? If for this example, is it correct? You will say no. Why no here? Because you see that the pre-order basically the in-order traversal for this particular example will be 3, and then 2, 4, 5, 2, 4, 5, then 1, and then 6, then 1 and then 6. So basically from 3 you are going to 2, from 5 you are going to 1, from 2 you are not going to 1, from 5 itself you are going to 1. So basically what you saw, from lefts, because earlier you were going from 2 to 1, but now I'm saying from left's extreme right you are going to the node itself. From left's extreme right you're going to 1. So you were going to left, that was good, but also go on to extreme right. That is what I'm doing right now. The only extra operation is go on to extreme right, and then you will, okay, you had that node, you had that pre, which is the left, you went on to extreme right, keep on going to the right until it is null, and then build a connection from pre's right to this current node. So pre's right to the current node. Now when this connection is done, now you have to just remove this link. For that I firstly assigned my temp to this value of 1, then I'll move my node to my left. Right now I will just say temp's left is null, a simple null, and that's how you will get this particular. Again, your pre will be pointing right now here, so your node will be pointing to this node, your temp is for sure here, which is this pre and temp are no more use, but you have built this connection which will help you in traversing and doing a Preorder traversal. Oh, sorry, Inorder traversal. Now the code is exactly what I have written right here. The code is exactly right here. Exactly. It is the only code. But bhaiya, that was the code when you are going left. But in the beginning, you told na that you will also go and go right. Yeah, as simple as that. The code which I showed you was the code when you have to go left. Right now, what if bhaiya left is null? Okay bro, if left is null, simply print the root node and then go on to the right node. That's it. If for the current node left is null, simply print the current node and go on to the right node. That's it. So that is if your left is null. If the left is there, then you have to perform the below operation, and that's how you can simply solve your in-order traversal. Again, the same can be applied for a pre-order, and a bit changes can be done and can be same use for post-order traversal also, and that everything you can do in a time complexity. And you will see space is for sure O of 1 because you are not using any extra space, because you are building the connection by yourself and you are not using memory to store the connections. Right, so the space is actually O of 1. But the time, you might think, bhaiya, what is the time complexity of this? We will see the time. I'll explain you time. But yeah, let's firstly code this up again. We will use the exact same code as what we wrote here. Let's go back and I'll keep on parallelly showing you the explanation also. But it's just not a much change. See, it's just simply that firstly we need to have the although you can use this root node also, but it is not a good practice to change the address of the root node itself. So I'll just copy this root nodes to this node value, which is the current node. Now, as you saw, I will only keep on going on to this current node while this is not equal to null. So while my current is not equals to my null, only then I should go. That makes sense. That is obviously makes sense. Now, as you saw that firstly, this is what we have to perform when actually I have my left node. So my case becomes when I don't have my left node. So I just simply say, bro, what you can do is you can just keep on assigning. Let's say I have a pre, because I for sure want a left node, so I just take as my pre. Now I just say it's roots left. Now if my pre is equals to my null PTR, then I know for sure that I should not go to my left, because I cannot go to my left. So simply do the current node, use the current node itself. So what I'll do, I'll just use the current node itself, as I did here itself. If you go back and see, then I just did use the current node and go on to right. I'll use the same stuff. Right, so what I'll do is I'll use the current node, which means I'll push back that current value in my answer. I'll push back the current value, which is current's value in my answer, and then I should go on to my right child, which is from current. I just simply go on to my right child, current's right. Now that is what is done when I had the I did not have the left. But bhaiya, what if I have the left? No worries, again simple. You will firstly assign your pre, that is already done, left node. Now keep on going the right, keep on going in the right. So what I'll do is while my pre's right is not equals to your null PTR, or you can also write the same thing as null. That is also working, but yeah, I use it as null PTR. Now while pre's right is not equal to your null, so I'll just simply keep on going in the right. Keep on going in the right. Now as soon as I have reached the right, so what should I do is I know that I have reached my extreme right, so I should assign pre's right to the current node, which is this current node. So I know that my current node was the node itself. I knew that my current node I should write, yeah, my current node, I have reached my pre, and this is my current, so I should assign my pre's right to the current node. Now this portion is done, pre's right to the current node, that is done. Now simply make a temp for this root current values. So I'll make a new tree node star, which is the let's say temp, and then I'll point to my current. Why I did that? Because I want that temps left should become null, because I cannot afford to maintain a loop in there. Now when this temps left has becomes null, but you still remember that you have that current node itself, just simply you can say just currents, and you can just move to left of the current node, because you should move to current nodes left, but you have simply assigned null. So firstly you should move left, and then lefts of that temp variable you should assign that to null. Now when this is done, we know that we have traversed on the entire tree. Now simply return the answer. Let's quickly see. We have an issue. Okay, so that was the current and not the root. The pre should be the current left and not the root. So yeah, let's quickly jump back and let's submit, and yeah, that's how you can simply get this solved. Now the time for this is actually O of n. How bhaiya O of n? Simply see, what you were doing was you were at 1, then you were at 1, your node was at 1, then you went on to 2, you went on to extreme right of 2 and then assigned that value, and then went on to 2 again. Now you went on to 3, you went on to extreme right of 3, which is nothing, then you went on to 2, then you went on to 4, 5, 1, and then 6. So you saw ultimately in simple recursion previously you were just simply going back, you were just simply doing what? You were going to 1, 2 and then coming back, which is 2 and 1. Here also you are just doing this operation, which is going to 2, then 3, and then going to 2, and then 4, and then 5, and then to 1. Same operation, like nearly same operation. The extra operation which you are doing is that as you go from 1, you go on to 2, you went on to entire right portion and then to 1, just to build a connection for this specific part, and you only went here, this entire portion specifically to build the connection, you only did it once. For all the nodes, for 2, 4, 5 and 1, you did it once to just build this connection. That's it. So for this, let's say you had this n nodes, you just use n operation, just n traversal to just build one connection. That's it, and that's what you wanted. So earlier your recursion was just going in and then moving backwards. The extra part here is you will go on to left and then extreme right to just build this connection. Again you'll go on to left, extreme right to build this connection, left, extreme right to build this connection. So you will see it is just that n nodes. Basically it is in total, if you have n nodes, let's say here I had 3 nodes, here I have 4, here I have 6 nodes. So basically in total it will be 3 plus 4 plus 6. So in total if I have n nodes, so I will be traversing n nodes in total, the extra nodes which I am traversing right now. So earlier if it would have been a O of n plus n, just an extra O of n is added and it will be still O of n, because it is just nothing but O of 3 into n, but still the time is still O of n. But as you're not using any in-memory spaces, so the space is O of 1, and that's how the time for this will be O of n and space will actually be O of 1, and that's how you will remember that how we build the entire problem. We build by a small, bigger and then bigger example. That's how you remember how to maintain the intuition. I hope that you guys got it. So goodbye, take care, bye bye.